Have you ever wondered why an explosion is over in a blink, but rust takes literally years to form on a piece of metal? Well, that's the whole world of chemical kinetics. See, thermodynamics can tell us if a reaction is even possible, but kinetics, that's where the action is. It tells us how fast it's going to go. So today we're jumping right into the science of speed, and you're going to learn how to master the pace of chemical reactions.
So what's the deal here? Is it an explosion or a slow evolution? What's the secret behind a reaction's speed? Is there some kind of universal speed limit, or is it something we can actually control? The amazing answer is yes, we can control it. And today, we're going to unlock those secrets and figure out all about these chemical speed limits.
You ready to get a handle on reaction speed? Okay, here's our game plan. We're going to kick things off with what rate even means in chemistry. Then we'll get into the nitty-gritty of the factors that actually control the pace of these reactions. We'll even crack the code on the math behind it, zoom in on the molecular action, and bust a few common myths along the way.
First things first, what do we really mean when we say rate? It's a lot like the speed of a car. It's all about how much something changes over time. But instead of miles per hour, we're usually talking about how much the concentration changes per second.
Okay, imagine you're on a road trip. Let's say it's 200 miles and it took you 4 hours. Your average speed was 50 miles per hour, right? You just divide the total distance by the total time. Well, that's exactly how we calculate the average rate of a reaction. We look at the total change in concentration over the entire time interval. It gives us a great big picture view of what's going on. But what if you wanted to know your speed at the exact moment you drove past a speed camera? For that, you'd glance down at your speedometer. That's your instantaneous rate. It's not the average over the whole trip. It's the precise speed of the reaction at one single moment in time.
So, what's the bottom line here? Think of the average rate like the highlight reel of the entire movie. It gives you the overall story. The instantaneous rate, though? That's the super slow-motion, frame-by-frame snapshot of a single critical moment. They both tell us something incredibly important, just from totally different perspectives.
Okay, so now we know how to measure the speed of a reaction. Let's get to the fun part. How do we control it? This is where we get to be in the driver's seat. There are 3 main levers we can pull to speed up or slow down pretty much any reaction. Lever number 1, concentration. It's pretty simple. The more molecules you pack into a space, the more often they're going to bump into each other and react. Makes sense, right? Lever 2, temperature. When you crank up the heat, you're giving those molecules a shot of energy. They start zipping around faster, colliding harder, and reacting more. A really cool rule of thumb is that the rate often doubles for every 10 degrees Celsius increase. And finally, lever 3, catalysts. Think of these as chemical matchmakers. They create an easier, faster path for the reaction to happen without getting used up themselves.
All right, let's talk about the math. But don't panic. The rate law isn't just some scary equation. It's better to think of it as the reaction's unique blueprint. It tells us, with amazing precision, exactly how those levers we just talked about, especially concentration, are controlling the speed. And get this, here's a wild fact about reactions that happen in multiple stages. You might think the total speed is just an average of all the steps, right? Or maybe it's set by the fastest step. Nope. The speed of the entire reaction is dictated by its single slowest step. This is called the rate-determining step, and it is the key to understanding everything.
Let's look at how nitrogen dioxide is formed. It actually happens in 2 steps. In step 1, 2 nitric oxide molecules come together. This happens super fast. But then in step 2, that new molecule has to react with an oxygen molecule. And this part is painfully slow. That slow step is the bottleneck. It's our rate-determining step, the RDS, and it sets the pace for the whole show.
Honestly, this funnel analogy is just perfect. Think about it. It doesn't matter how wide the top of the funnel is or how fast you pour water in. The speed of the water coming out the bottom is always going to be limited by that one single narrowest point. The slow step in a reaction, it's that narrow point. It sets the maximum speed, period.
Okay, now listen up, because this table right here is basically a cheat code for your exams. The rate constant K, that letter in our rate law blueprint, has different units depending on the reaction's order. Just look at that middle row. For a first-order reaction, the unit is just per second. If you see that on a test question, you instantly know the reaction order, no math needed. This is an absolute game changer.
So, we've covered the what and the how, but now for the really cool part, the why. Why do things like temperature and concentration even make a difference?
To get that, we have to zoom way, way down to the molecular level and actually watch what's happening when these molecules collide.
You see, for a reaction to actually happen, molecules can't just gently bump into each other. Two things absolutely have to happen. First, they need to slam into each other with enough energy to break their old bonds. We call this minimum energy the activation energy. And second, they have to hit each other in exactly the right way, with the right parts lined up, kind of like two puzzle pieces clicking together. If you're missing either the energy or the right orientation, they just bounce off each other. No reaction.
Now don't let the equation on the screen freak you out. The Arrhenius equation is really just a beautiful, compact way of putting it all together. It shows that the reaction speed, which is that K value, is basically controlled by two big things: the size of that energy barrier, the EA, and the temperature, T. The hotter it gets, the more molecules have enough juice to leap over that activation barrier and make the reaction happen.
And this brings us right back to catalysts. So how do they work their magic? Well, a catalyst is kind of like building a tunnel through a mountain. The start and end points are the same, but the journey is so much easier because you don't have to climb all the way over the peak. It just provides a totally new pathway with a lower activation energy. That's exactly how the catalytic converter in your car works, and it's how enzymes in your body speed up reactions millions of times faster than they'd ever happen on their own.
Okay, let's head into the home stretch. In this last section, we're going to tackle some of the most common mix-ups and give you some seriously useful tips to make sure you nail these concepts when it really counts.
This is probably the #1 biggest misconception in all of chemical kinetics. I mean, it kind of feels right, doesn't it? You add heat, things go faster. So you must be making that energy hill smaller, right? But is that actually what's going on?
And the reality is a definite no. The activation energy is a fixed property of that reaction. It's like a wall that's a certain height. Raising the temperature doesn't make the wall shorter. What it does is give more of the molecules the energy they need to jump higher, so a bigger chunk of them can successfully get over that same wall.
Okay, here's another one that trips people up. We know reaction order can sometimes be 0 or a fraction, which is weird. But what about molecularity? That's just the number of molecules that physically collide in a single step. Can you have half a molecule in a collision?
And again, a big no. Think about it. Since molecularity is literally counting the number of particles smashing into each other, you can't have half a molecule show up to the party. You can't have 0 molecules collide and make something new. It has to be a positive whole number, almost always 1, 2, or very rarely 3.
Let's wrap up with that killer exam tip one more time, because seriously, it's that important. Before you even start a complicated problem, just stop. Take a breath and look at the units of the rate constant K. They are a dead giveaway for the reaction order. They'll save you so much time and help you avoid simple mistakes. You should definitely burn this slide into your brain.
So, we've pulled back the curtain on the how and why of reaction speed, but the real takeaway is to start thinking about the where. I mean, from designing life-saving medicines and creating industrial catalysts to understanding the atmospheric chemistry that drives climate change, mastering kinetics isn't just for a test, it's one of the most critical challenges we face today. Because ultimately, the power to control speed is the power to shape our world.